Hey guys, this is the CAD model of a 2012 Nissan Navara center console bezel. I created it from the 3D scan I showed in my previous video. In this one, I will walk you through the complete reverse engineering process of a car console, step by step from start to finish. This bezel isn't the original part. It's an aftermarket one that's been modified to fit a 9-inch Android screen. That's why I think it's fine to share the point cloud scan data so you can follow along with this tutorial. In this tutorial, I will be using BricsCAD, one of the best CAD tools for reverse engineering, whether you are working on mechanical parts or buildings. BricsCAD is one of the few CAD platforms that can import point clouds directly without add-on or extra subscription. For complex parts like this, mesh data just isn't enough. You won't be able to fully reverse engineer with it. You need a CAD tool that works natively with point clouds. After importing the point cloud, I will align the scan data to the X, Y, and Z axis by snapping the straight edges of the model to horizontal and vertical lines. Since this bezel is symmetrical and built around a square and rectangular geometry, this alignment step is crucial for achieving an accurate final result. By the way, you will find the point cloud download link right in the description so you can follow along. The bezel's geometry has been shaped by cutting to form its profile. I have rotated it to the side here so I can trace the original outline more accurately. This console was originally designed with a very basic shape. From what I can see, it was built using only two cross-sectional profiles. I have positioned the cross-sectional sketches I traced. The two on the right share the same profile, while the one on the left is slightly smaller. You can create a lofted surface by selecting the two polyline sketches. Lofting one section at a time won't give you a smooth surface, and this is what I want for these two first sections. At this corner, a fillet won't work. The profile just doesn't match. Instead, I will crop a thin slice of the point cloud in this area and create two additional cross-section sketches. I do this by simply copying the original sketch profile and offsetting it downward. When you loft more than 3 cross-sections at once, the surface comes out smooth, and in this case, the curve matches the point cloud perfectly. This is where everything starts to take shape. CAD builds models from sketches, whether 2D or 3D lines. Unlike polygonal tools such as Blender or 3ds Max, which create models by manipulating polygons. Even though you see those rectangular grids, they are not mesh. CAD surfaces are defined by mathematical equations, which mean they have infinite resolution and can be modified without losing accuracy. It's always a mistake to start CAD modeling by wrapping surfaces from scan meshes. Those over-advertised reverse engineering software packages won't take you very far. Once you face more complex parts, you will quickly hit a wall. Next, I will create the patch surface by selecting the boundary sketches. Then I extract the edges from the surface so I can cap and close all sides, making the model completely watertight. Now these watertight surface shells are ready to be converted into a solid. I use the stitch command to turn this into a solid. Technically, you could loft each closed-loop sketch profile directly into a solid from the start, but I wanted to demonstrate this alternative approach. Next, I will hollow out the solid using the shell command. I have opened two faces and set the wall thickness to 3.2mm. That's thicker than the original, but for a part this large, the walls should be at least 3mm to ensure reliable FDM printing. This modeling approach is the same method used when the bezel was first created. Next, I will create the sketch to cut out the side wall. I will crop a thin slice of the point cloud in this area, trace the lines, and form closed loop sketches. For a quicker method, you can simply extrude polylines into a surface and use that surface to slice the solid. This approach is faster when trimming complex geometry. This corner is a bit tricky to trim. The solid has a rounded corner making a turn, while the cutting profile lies in a 3D space. There is no flat plane here, so I create vertical line segments that match the height of the cutting profile running along the round corner. Then I draw lines and arcs along the tips of those vertical segments to create 3D curves. The 3D lines are placed slightly wider than the wall to be cut, and I also create matching 3D curves for the inner wall. Then I use the outer and inner wall 3D curves to loft a surface, which I apply to slice the solid. The result is a very clean cut, even better than the original part, which relied on multiple extrude cuts across different planes. That method is slower and produces poorer results. I use the same approach for the other corner. This workflow also works in Autodesk Inventor, and most major professional CAD software can trim solids with surfaces. Next, I will make another cutout. I trace a line along the cutting direction, use that line to set up a UCS, and then create a sketch profile on that UCS. This ensures both the correct profile and the proper cutting angle. Again, I trim this section by slicing with a surface. This will be the AC control panel mounting. It includes a support wall extruding inside, and the walls are tapered. So before trimming, I will first create the support wall using a solid loft. On the edge of the support wall, I offset the cross section to create the cutting profile, then use it to extrude cut the bezel. Now I have a frame with a small step just like the original part. I then union the support wall with the bezel. Because the joint between the support wall and the bezel is very thin, I add a fillet to increase the thickness along this joint. Next, I create a cutout for the emergency light button. I use the 3-point UCS to snap onto the surrounding surface of the circle and build the cutting sketch profile. Then I round the cutting edge with a 1mm fillet. I apply the same approach for the air grill loader cutout. Since the wall is very thin, I use a 3-point UCS to snap onto the surrounding surface and determine the cutting angle. There is a symbolic emboss here, so I press it down by 0.5mm. Next, I'm going to model the display mounting frame. Since it has a taper wall with different angles on each side, I built it using a solid loft. Then I use the push-pull command to create the inner wall. Next, I create loft profiles to define the vertical walls of the display frame. Then I hollow it out using the shell command, removing 3 sides and setting the wall thickness to 2.5 mm. Then I use the subtract command to remove the bottom side of the vertical wall. After subtraction, you need to apply the separate command before you can delete the bottom half. Next, I reuse the old vertical wall sketches, offsetting them 2.5 mm inward to form the inner wall. With that profile, I perform a loft cut on the bezel. I use the separate command to remove the remaining solid body. Next, I will union all the bodies together into a single solid. So we have already reached the 10-minute mark. If you are still watching, it means you are genuinely interested in reverse engineering. Next, I will model the rest of the display frame. This part is straightforward. Just sketch the profile and use the push-pull command to form it. The push-pull and manipulate commands in BricsCAD can really speed up the modeling process. The software automatically detects a closed-loop sketch on the surface, so you don't need to trim or join the lines to use this function. Next, I create the fan grill cutout. Since the cutting angle aligns with the XY plane, I simply move the UCS onto it and perform an extrude cut. Next, I create the cosmetic emboss, a strip with a groove about 1 mm deep. I sweep a circular profile along the curved part. The tricky part here is generating the 3D curve directly above the surface. First, I extrude a surface from a flat sketch. Then I use the imprint command, select the surface first and then the bezel. This command creates an imprint on the surface. Then I use the extract edge command to pull 3D lines directly from that surface. The 3D lines lie exactly above the solid surface, which makes them perfect as sweep parts for cutting the embossed profile. Next, I select the edge along the cutting groove and round it with a 0.5 mm fillet, making the embossed line smoother and slightly wider. At the top of the bezel, I draw 2 lines to close the profile, then use the push-pull command to cut open the glove box. Next, I use the unequal length chamfer to adjust the surface shape here. And here I add one small extrusion. And here I extrude the vertical wall for the glove box. From this point onward, the modeling becomes easy. Just a few sketches combined with the push-pull command. I would say the most difficult part was figuring out how the original designer began this model. It took me a while to realize they start with a simple loft sections. By nature, designers avoid complicating things. Most will begin with a simple shape. So in reverse engineering, a common practice is to figure out the very first command in the modeling sequence. After that, everything becomes easier. This workflow touches nearly all of BricsCAD's modeling commands. A beginner should practice with UCS because sketches always start on the XY plane. Mastering how to reposition the UCS is essential for placing sketches exactly where you need them. Now moving on to the back side, there are several mounting clips to model here. The clips point in different orientations. To determine the correct extrude direction, I adjust the viewport until the point cloud wall aligns, then use a UCS view to set the sketch plane. I also move the UCS to the required depth by snapping it onto the point cloud. For this clip, I will demonstrate trimming it to the curved surface using the slice command. You can extract the surface from the solid and use it for slicing, but in this case, the subtract command is faster. The clip profiles has a simple shape, so I use the push-pull and manipulate commands to model them directly onto the solid faces. The manipulate command is a powerful tool. It lets you set angles on any flat surface in just a few clicks. And just like that, the first clip is finished in no time. This part is a bit tricky. It's the frame for the fan grill. I start by extruding it as a solid, then subtract it from the bezel. Here I notice a wall I miss and remove it. The fan grill pocket has 3D curved edges, so it needs to be trimmed with an extrude surface. I had to trim it twice to get the final shape. There are 4 clips for the fan grill, and luckily they share the same shape. I simply model them using the push-pull and manipulate commands. I copy the clip to the second location and simply use the push-pull command to adjust its height. I mirror the clip and move it to the opposite side and adjust the height. And here is the final one. Now all 4 clips are in place. Next, I will trim the 4 clips flush with the curved surface of the bezel using a simple subtract command. After subtraction, I use the separate command to select and delete the unwanted bodies. The subtract command has an option to keep the cutting body. It's called delete to. Just type in the command line and enable it. On the side wall, there is a thin clip that isn't rectangular. Creating the lock key is a bit tricky, and it has to be formed by lofting. This clip extends beyond the flat sidewall surface that I plan to place on the build plate, so it may need to be printed separately. I use UCS view to align the XY plane for the screw mounting hole sketch. Then UCS move to snap the point cloud onto the top mounting face. The solid above the stiffener has to be clear to match the scan data, while the solid below can be tapered for strength. I taper the cylinder by 5 degrees and ignore the thin stiffener. Those are meant for injection mold parts. For FDM printing, we can print hollow, so I will use the tapered cylinder instead. I really like the subtract, split, and separate commands in BricsCAD. They make modeling this console much quicker. In Autodesk Inventor, trimming clips flush with a curved surface takes far more clicks. And you will find a lot of clips like this in automotive plastic part. This half of the console bezel has 19 clips. Luckily it's symmetrical, so I only need to model one half. For reverse engineering a symmetrical part, you need a high precision laser scanner. The river point laser scanner that lacks the accuracy for this task. When you mirror your CAD model, the mirror side will never align with the point cloud on the opposite half. Here's the final clip of the console. I will copy it from the opposite side and modify it to fit this location. This clip has stiffeners on both sides, so I will use the slice command to separate the stiffener and then mirror it to the opposite side. If you are still watching after 20 minutes, it shows you have a strong interest in reverse engineering automotive parts. I export one half in step format and open it in FreeCAD. It loads without any issue and every detail appears as if it were modeled directly in FreeCAD. If I print half of the bezel, it will fit on my K2 Plus build plate. However, I won't be doing the printing in this video. I first need to design a proper mechanical joint to connect the two halves securely. The bezel is very thin and even the original injection mold part already feels flimsy. Each half will take over 10 hours to print, so I only get one shot at trying. I will need some time to figure out how to join a bezel this thin, but I already have a few ideas in mind. I've been using CAD professionally for over 27 years, almost every day. From that experience, I can confirm BricsCAD is one of the best tools for reverse engineering. Even though I have only used it for 2 months to create a YouTube content, its capabilities really stand out. Like with every manufacturer, no one pays me to make these videos, and I never earn a commission from software or product sales. If something is bad, I will say it's bad. If it's good, I will say so. Thanks you guys for watching. I'll see you in the next video.